Welcome to Mythos AI, your source for Cliff's Notes on complex subjects. Join Anna and Phil for yet another engaging conversation.
Welcome to our deep dive into the world of quantum computing.
Yeah.
We have a collection of research articles and reports all about this
Yeah.
fascinating emerging technology.
Cool.
Our mission today is to distill the most important information for you, so you can walk away with a solid understanding of this revolutionary field.
It's a field that really challenges our conventional understanding of how computers work. It requires us to delve into the strange and counterintuitive world of quantum mechanics.
Okay, so let's start with the fundamental question. What makes quantum computing so different from the computers we use every day?
At the heart of this difference lies the way information is processed. Classical computers, the ones we're all familiar with, rely on bits. A bit is like a switch that can be either on or off, representing 1 or 0. Everything you see on your computer screen, every calculation performed, is ultimately based on the manipulation of these bits.
So our laptops, smartphones, even the most powerful supercomputers are all essentially built upon this simple foundation of bits.
That's right. But quantum computers introduce a completely new concept, the qubit. Unlike a bit, which can only be in one state at a time, a qubit can be in a superposition of states. It's like a coin spinning in the air before it lands. It's not heads or tails, it's in a state that encompasses both possibilities simultaneously.
So a qubit can be both 0 and 1 at the same time. That's pretty mind-bending.
It is. This ability to exist in multiple states simultaneously is one of the key principles that gives quantum computers their immense power. Think of it this way. If you have a classical computer with 4 bits, it can be at only one of 16 possible combinations at a time. But a quantum computer with 4 qubits can be in all 16 combinations at once.
That means a quantum computer could explore many possibilities simultaneously, while a classical computer would have to plod through them one by one.
Exactly. Imagine searching a maze. A classical computer would have to try each path sequentially, backtracking if it hits a dead end. A quantum computer, thanks to superposition, could, in a sense, explore all paths concurrently, finding the solution much faster.
That's a powerful advantage. And this brings us to another key concept in quantum computing: entanglement.
Entanglement is a phenomenon where 2 or more qubits become interconnected even if they are physically separated. Their fates are intertwined in a way that defies our classical intuition. When you measure the state of one entangled qubit, you instantly know the state of the other, no matter how far apart they are.
So it's as if these qubits are communicating with each other instantaneously across any distance. That sounds like something out of science fiction.
It does, but this spooky action at a distance, as Einstein called it, is a fundamental aspect of the quantum world. In a quantum computer, entanglement allows qubits to work together in a highly coordinated way, dramatically increasing the complexity of calculations they can perform.
So we got these qubits in superposition, entangled together, capable of performing calculations on multiple possibilities at once. How do we actually control and manipulate these qubits to perform useful computations?
That's where quantum gates come in. They are the building blocks of quantum circuits, analogous to logic gates in classical computing. But instead of manipulating bits, quantum gates act on qubits, manipulating their superpositions and entanglements.
So you're essentially choreographing the interactions between these entangled qubits to carry out specific computations.
Precisely. Designing these quantum circuits is a complex task that requires a deep understanding of quantum mechanics and sophisticated mathematical tools. It's like composing a delicate quantum ballet where each gate performs a specific move, guiding the qubits through a series of transformations.
And just like in a ballet, timing and precision are crucial. A slight error in the sequence of gates can completely derail the computation.
Exactly. And that brings us to one of the major challenges in quantum computing: decoherence. Qubits are extremely fragile and susceptible to environmental noise. Any interaction with the outside world can disrupt their delicate quantum states, causing them to lose their superposition and entanglement.
It's like trying to balance a spinning coin on its edge. Any slight vibration will cause it to topple over.
That's a good analogy. Decoherence is a major obstacle to building practical quantum computers. Scientists and engineers are constantly working on ways to shield qubits from their environment, using techniques like supercooling and magnetic shielding.
So building a quantum computer isn't just about assembling the right components. It's also about creating an environment where these qubits can maintain their quantum properties long enough to perform useful calculations.
Absolutely. And even with these sophisticated shielding techniques, Decoherence is still a major factor limiting the performance of current quantum computers. It's one of the reasons why quantum computers are still in their early stages of development.
It's clear that building a quantum computer is a formidable engineering challenge, pushing the boundaries of what's currently possible. But let's assume we've managed to build a stable quantum computer with qubits in superposition and entanglement, manipulated by precisely choreographed quantum gates. How do we actually get an answer out of this quantum system?
That's where quantum measurement comes in. Remember that qubits exist in this hazy state of superposition until we observe them. Measuring a qubit forces it to collapse from its superposition into a definite state, either a 0 or a 1.
So the act of observing the qubit forces it to make a choice.
In a way, yes. And the outcome of this measurement is probabilistic. We can't predict with certainty whether a particular qubit will collapse to a 0 or a 1, but we can calculate the probabilities based on the qubit's superposition.
So unlike classical computing, where the output is deterministic, quantum computing introduces an element of randomness.
That's right. And this probabilistic nature has profound implications for how quantum algorithms are designed and executed.
This has been an incredibly insightful overview of the fundamental principles of quantum computing. We've covered a lot of ground, from the nature of qubits and superposition to entanglement, quantum gates, and measurement, but this is just the beginning of our journey into the quantum realm. We've laid the foundation for understanding how these strange and counterintuitive concepts can be harnessed to perform computations that are impossible for even the most powerful classical computers.
And in the next part of our deep dive, we'll explore the different ways quantum computers are being built and the incredible range of applications they promise to unlock. From revolutionizing drug discovery and material science to breaking encryption and transforming artificial intelligence, the potential impact of quantum computing is truly mind-boggling.
Now that we have a solid grasp of the fundamental principles of quantum computing, let's dive into the different models being developed to harness the power of these mind-boggling concepts.
There are three primary models of quantum computing: gate-based quantum computing, quantum annealing, and topological quantum computing. Each approach has its strengths and weaknesses, and they are suited for different types of problems.
Let's start with gate-based quantum computing, which you mentioned is the most common model.
In gate-based quantum computing, we manipulate qubits using a sequence of quantum gates, much like how classical computers use logic gates to manipulate bits. These quantum gates can create superpositions, entangle qubits, and perform a variety of other operations, essentially orchestrating a complex dance of quantum information.
It sounds like programming a quantum computer is like composing a musical score where each gate represents a note or a chord.
That's a good analogy. The sequence and timing of these gates are crucial to performing the desired computation. It requires a deep understanding of quantum mechanics and advanced mathematical tools to design these quantum algorithms.
And you mentioned companies like IBM and Google are at the forefront of this approach.
Yes, IBM has made significant progress with its superconducting transmon qubits. These qubits are essentially tiny circuits that operate at extremely low temperatures, just a fraction of a degree above absolute zero. Google, on the other hand, is using superconducting transmon qubits as well, but they are exploring different architectures for their quantum processors.
So even within the gate-based model, there are different approaches and technologies being explored.
Absolutely. The field is still rapidly evolving, and there's a lot of competition and collaboration happening as researchers and companies race to build the most powerful and reliable quantum computers.
Now, what about quantum annealing? How does this model differ from the gate-based approach?
Quantum annealing is a specialized approach that excels at solving optimization problems. Think of it like finding the lowest point in a complex landscape. A classical computer would have to search every nook and cranny, which can be incredibly time-consuming.
So it's like trying to find the best solution out of millions of possibilities, like the most efficient route for a delivery truck or the optimal configuration for a financial portfolio.
Exactly. Quantum annealing takes advantage of a phenomenon called quantum tunneling. Essentially, the qubits can tunnel through energy barriers, allowing them to quickly explore different configurations and settle into the lowest energy state, which corresponds to the optimal solution.
So instead of painstakingly searching through every option, quantum annealing lets the system naturally evolve towards the best solution.
That's a good way to put it. And D-Wave Systems is the leading company in this field. They have built specialized quantum annealers that are already being used to solve real-world optimization problems in areas like logistics, finance, and materials science.
It's amazing to see how this specialized approach is already finding practical applications. Now let's move on to the third model you mentioned, topological quantum computing.
Topological quantum computing is a more recent and arguably more ambitious approach. It aims to address one of the biggest challenges in quantum computing: decoherence. Remember how we talked about qubits being incredibly fragile and susceptible to environmental noise?
Yes. Decoherence is like the Achilles heel of quantum computers.
Exactly. Topological quantum computing tries to overcome this problem by encoding information in a more robust way. It utilizes special types of quasi-particles called anyons, which exist in two-dimensional systems. These anyons have unique properties that make them less susceptible to decoherence.
So instead of relying on the delicate state of individual qubits, topological quantum computing uses the collective behavior of these anyons to protect information.
Precisely. It's like weaving a tapestry where the information is encoded not in individual threads, but in the overall pattern of the weave. This makes the information more resistant to disruptions.
It sounds like a very elegant and potentially powerful approach.
Yeah.
But is it just theoretical, or are there actual efforts to build topological quantum computers?
Microsoft is one of the leading companies investing heavily in topological quantum computing. They believe this approach has the potential to lead to more scalable and fault-tolerant quantum computers. However, it's a very challenging area of research, and we are still many years, if not decades, away from seeing practical topological quantum computers.
It's fascinating to see how different approaches are being explored to unlock the potential of quantum computing. We've got gate-based systems like those being developed by IBM and Google, focusing on general-purpose quantum computation. We have quantum annealers from D-Wave, specializing in optimization problems. And then there's the more futuristic topological approach being pursued by Microsoft, aiming to overcome the limitations of decoherence.
Each of these models has its own strengths and challenges, and it's likely that the future of quantum computing will involve a combination of these approaches. We might see hybrid systems that leverage the best of each model, depending on the specific application.
So we have this diverse landscape of quantum computing models, each pushing the boundaries of what's possible in computation.
Yeah.
But the real excitement, of course, lies in the potential applications of this revolutionary technology.
Absolutely. Quantum computing has the potential to revolutionize a vast array of fields, from medicine and materials science to artificial intelligence and cryptography. The possibilities are truly mind-boggling.
We've delved into the intricate world of quantum computing, exploring its fundamental principles and the diverse models being developed. Now let's shift our focus to the potential applications of this revolutionary technology. The areas where quantum computing is poised to make a significant impact are vast and incredibly exciting.
It's true. One of the most talked about applications is in the field of cryptography. As you know, the security of our online transactions, communications, and sensitive data relies heavily on encryption algorithms. These algorithms are designed to be incredibly difficult for classical computers to break. But a sufficiently powerful quantum computer running Shor's algorithm could crack these codes wide open.
That sounds like a serious security threat.
It is. A quantum computer capable of running Shor's algorithm efficiently could potentially compromise the entire digital infrastructure we rely on today. From online banking and e-commerce to secure government communications and military secrets, everything could be vulnerable.
So does this mean the future of cybersecurity is bleak in the face of quantum computing?
Not necessarily. Quantum mechanics offers not just a threat, but also a solution. Quantum key distribution, or QKD, utilizes the principles of quantum mechanics to create theoretically unbreakable encryption keys. QKD relies on the fact that any attempt to eavesdrop on a quantum communication channel inevitably disturbs the delicate quantum states of the photons being transmitted. This disturbance is immediately detectable, alerting the parties involved to the presence of an eavesdropper.
So it's like a tamper-proof seal for digital information.
Precisely. While quantum computers pose a threat to classical encryption methods, they also offer a pathway to a new era of ultra-secure communications. The development and deployment of QKD technologies are crucial to safeguarding our digital world in the quantum age.
It's fascinating how quantum computing presents both a challenge and an opportunity in the realm of cybersecurity. Now let's move beyond cryptography. What other fields are ripe for a quantum revolution?
Drug discovery and materials science are two areas where quantum computing holds immense promise. Imagine being able to design new drugs and materials at the molecular with unprecedented accuracy.
That sounds like science fiction.
It might seem that way, but it's becoming increasingly within the realm of possibility. Quantum computers can simulate quantum systems, such as molecules, far more efficiently than classical computers. This is because they operate using the same principles that govern the behavior of these systems. Classical computers struggle to simulate quantum phenomena accurately due to the exponential growth in complexity.
So quantum computers could significantly accelerate the process of drug discovery and materials design.
Exactly. They could enable researchers to screen vast libraries of molecules to identify potential drug candidates, simulate the properties of new materials, and design optimized catalysts for chemical reactions. This could lead to breakthroughs in medicine, manufacturing, and energy production.
The potential impact on human health and technology is immense. Now, we've talked about quantum computers excelling at optimization problems. Can you elaborate on how this capability can be applied to real-world scenarios?
Think about the complexities of global supply chains, traffic flow in megacities, or even financial markets. These systems involve countless variables and intricate interdependencies. Classical computers often struggle to find optimal solutions for these types of problems, but quantum computers, with their ability to explore vast solution spaces simultaneously, could revolutionize how we manage these complex systems.
So we're talking about a world with more efficient logistics, smoother traffic flow, and perhaps even more stable financial markets.
It's certainly a possibility. Quantum algorithms for optimization problems are being actively developed and tested, and we are already seeing promising results in areas like route planning, resource allocation, and portfolio optimization.
It's exciting to envision a future where quantum computers help us tackle some of the most challenging optimization problems we face today. Now let's turn our attention to another area where quantum computing is making waves: artificial intelligence.
Quantum computing has the potential to supercharge artificial intelligence in a number of ways. One key area is machine learning. Quantum computers could significantly accelerate the training of machine learning models, allowing us to process vast data sets and develop more sophisticated algorithms.
So we could see AI systems that learn and adapt much faster, leading to advancements in areas like image recognition, natural language processing, and predictive modeling.
Precisely. Quantum machine learning is a rapidly evolving field, and researchers are exploring various quantum algorithms for tasks like classification, clustering, and regression. Another area where quantum computing could benefit AI is in optimization. As we discussed earlier, quantum computers excel at finding optimal solutions. This capability could be applied to optimize the parameters of neural networks, making them more efficient and accurate.
It's fascinating to think that quantum computers could enhance both the speed and the intelligence of AI systems. We've covered a wide range of applications from cryptography and drug discovery to optimization and artificial intelligence. It seems like quantum computing has the potential to touch almost every aspect of our lives.
It's true. And we've only scratched the surface. New applications are constantly being explored, and the full impact of quantum computing is still unfolding. It's an exciting time to be involved in this field.
As we conclude our deep dive into the world of quantum computing, it's clear that this technology has the potential to revolutionize our world in profound ways. From solving complex scientific problems to transforming industries and enhancing our daily lives, the possibilities are vast and inspiring.
However, it's important to remember that quantum computing is still in its early stages of development. Many challenges remain, including building larger and more stable quantum computers, developing practical quantum algorithms, and addressing ethical considerations.
It's a journey that requires continued investment, collaboration, and innovation. But the potential rewards are so significant that the pursuit is well worth the effort.
As we move forward, it's crucial to foster a deeper understanding of quantum computing among the public and to ensure that its development and deployment are guided by ethical principles and a commitment to societal benefit.
Quantum computing is not just a technological advancement, it's a testament to human ingenuity and our relentless pursuit of knowledge. It's a field that will continue to challenge our understanding of the universe and push the boundaries of what's possible.
And as we venture further into the quantum realm, we can expect even more astonishing discoveries and transformative applications that will shape the future of humanity.
Thank you for joining us on this deep dive into the fascinating world of quantum computing.
It's been a pleasure sharing this journey with you.
Thanks for listening to Mythos AI. Stay tuned for more concise insights. And remember to hit the like button and subscribe for future episodes.